All right, so I'm going to talk about the monomethyl hydrogen and nitrogen tetroxide combustion that's used for rocket fuel. So this is just a video of it in action on a
Okay, I'm going to get the pro. 99, proceeded, 3, 2, 1, ignition. Right away, Houston. Vector good. X thought.
So it is, the combustion reaction is really good and produces a lot of energy, but it is extremely toxic for humans, so it's usually used for unmanned type rockets on
Mission arm is out.
or like missiles or some sort if they're going that way. And
The pipette is there for a reason. I don't want my hands anywhere near this thing.
it's really quick, and it is definitely very reactive.
You can really see there is this very fast reaction which generates loads of nitrogen and also ethane. And so all of the products here are gaseous, and you get a tremendous expansion. At the same time, because it gets very hot, it glows so brightly and produces a pipette is there.
So what were the components in this explosive stuff?
That's the monomethyl hydrogen, and then I think it's nitrogen dioxide. It's a nitrogen tetroxide.
Mm-hmm.
So then the potential energy that's used to get this going is it comes from, as the monomethyl hydrogen, these guys are oxidized by the nitrogen dioxide. And here's a little video of that happening. It's kind of showing it. So as these break apart and come together, those bonds breaking is what causes the energy. And then on this side is just the different energy levels that happens as the molecule is oxidized.
What levels? Total energy.
Total energy, I mean, yes.
And for specifically for Joseph, where is the proton that is getting transferred?
The proton that's getting transferred is...
Which color for the proton is used?
it should be red.
Red is oxygen, blue is nitrogen.
Yep.
What is color for proton?
brown.
Dark is brown is probably for carbon.
Carbon, okay.
What other colors are there?
White.
Okay, so white is for
Oh,
carbon.
yeah, that's the hydrogen.
So,
yeah.
so which hydrogen is being transferred? Can you point by finger?
Should be right in this area. No.
Another? Lower? Yeah.
Oh, okay. Oh, yeah.
So there is
a
a reactant, and what is the product? Just on the same figure by finger.
Yep.
Product, last image.
So
where is this proton getting transferred to?
it's getting transferred to up here.
No, to oxygen, to red.
Oh, yeah. Yeah.
Okay. For positive grade.
So this is just setting up the code. So h bar is equal to 1, the mass of the proton in atomic units. This is the frequency of the proton's oscillation. P naught is what is being changed throughout the experiment, width of the initial wave packet, and the time step, and the number of time steps. The more time steps would be a better representation, but it takes longer for the code to run. So then this is just an example of the code running. I think this is about 30 momentum. So red is your reactants, and then green is your activation energy. Blue is your products. So as it goes on, products comes out, and it just, as the reaction goes, it settles out. This goes on for quite a while, but. So a big discovery when I was running the code is this reaction can happen at room temperature, as shown by the video earlier. So normally, under classical physics, your reactance isn't above the activation energy. So under classical physics, the reaction shouldn't go. But because of, I have a table of probability of the slopes, it's a non-zero probability slope. So the reaction does go. And this is due to quantum tunneling. So not as much of the reaction, you won't get as much products, but the reaction still goes due to quantum tunneling. And this is just the temperature and activation energy at various momentums. This is in this area, I should add more data points, but in this area, as the temp, is when this will happen. So at like room temperature and stuff, so like in like the 15, 16 momentum area. So then this is just the different momentum of graphs. So at zero momentum, your electron, the probability where you find your electron is pretty straightforward. It's not really moving. And your probability of your products is very little in reactants, so it's not going forward at all. And then this is just slowly as you increase the momentum, your probability of the reactant on your products is going up and reactants. And as you can see, the line on the bottom here, where you find the electron, is getting a little more curved, so it's moving more. And then this is at 3.1 momentum, as the slopes are increasing, and your position of where you find the electron is going away. And then this is like quantum tunneling area as it goes. And then 6.2. So like I said, it just keeps increasing as the momentum increased and the temperature increased. So then this is where you start to see where the reaction will go as the slope of the probability increases, and you get your probability of finding the electron. And as it just keeps increasing, as you increase the momentum. And this is about where I have the highest probability and slope. As you can see, the slope is very deep or large compared to the other ones. And the probability where you find your electron, it goes off, so as your products, reactants are turning into products. And then as you start increasing momentum past this point, it started to go back. As your slope starts to change less, it becomes lesser than that. And as you can see, it just keeps going as this turns back into more of a straighter line. Saying that, and then 80, and 90, and went back to it again. And then, so when you're at about 70 momentum here, it looks more like the momentum graphs at like 0 momentum, 1.87 momentum. It's more of a straight line. So you don't have as much product being, reactants and products being turned into. So that just kind of follows it, and then just kind of goes back and forth as reactants and products are turned as the momentum is changed. So that's the 100 momentum. And then this is just the slope of the probability of the graphs of these graphs. This is your products, so those graphs. And this is just the slope quantized. So as the momentum increased, your slope was increasing, meaning more reactants was turning into products. And this is right in this range is when you have a non-zero probability of the products, which means that the reaction still goes even though it's not above that activation energy. So that's due to the quantum nature of the particles going through. And that's about it. So.
Okay, let's thank you. So, questions. 100 atomic units of momentum.
Yeah.
Which temperature or which energy would it correspond to?
So that was, when you get that high, the temperature is like just ridiculous. So when
how does it correspond? Yeah, sure. How does it correspond to temperature on surface of sun and temperature of nuclear explosion?
It's like similar to the temperature of the sun, especially when you're at this 40 momentum. I mean, that's 12,000.
It's about three times bigger.
Yeah.
3 times bigger.
Yeah, so I mean, you're never going to get that.
So it means like your spacecraft lands on the sun?
Yeah, pretty much. So, yeah.
Oliver has a question.
So you flip between electron and particle. What is this actually simulating? Is it a proton transfer or an electron transfer?
Proton transfer. I say electron before. I didn't.
Yeah, sometimes.
Oh, sorry, my bad.
So
definitely proton.
What would happen if you were trying to use these simulations for any other atom in your system other than proton? So like carbon or nitrogen or oxygen?
So you would have more mass, which would affect.
Exactly. Perfect
Yeah.
answer.
You would have more mass, so that would affect the kinetic energy and stuff.
So would you assume that the tunneling is still highly probable?
I would assume the tunnel, yes, because when you do it in real life, like the reaction still goes, and that's using nitrogen instead of just a single proton. It's probably not as probable at that large of a mass, but it still does happen. Yeah, I hope that answers your question.
More questions to Joey? If not, thank you once again. And we have 20 minutes for 2 talks. So